Anyway, okay, thank you for your kind cooperation. Okay, so now I'd like to continue the lecture. And in the last lecture, maybe I went through all the, yes, okay. Uh-huh. So I went through all the spin satellite stabilization, and after that, we started bias momentum system, bias momentum stabilization. Okay, and we just started the initial part of the bias momentum, stabilization equation. Okay, and so now I'd like to. Some part is already I showed you in the last lecture. Maybe I already like this. And so this is the internal, momentum around the XYZ axis. And internally, only the one wheel is usually installed in the y-axis. And so only the y has the, internally biased momentum. And so this minus h can be written as, okay, IW large omega. IW means moment of inertia of the wheel around the y-axis, and the large omega is wheel speed. This is the rotational speed of the wheel. Wheel speed. Okay, and the angular momentum around the y-axis is multiplication of the IW and the large omega. So now we have several assumptions. So we are now using the principal frame. Body frame is a principal frame. That is IXY, IYZ or something is 0. Okay, principal frame assumption. And the and body frame is aligned with orbital frame. That means the orbital frame is objective. That is idealistic situation. That okay. So that is a target. Orbital frame is a target. That means x-axis, z-axis of the body frame should be aligned with direction toward the nadir. Nadir means the center of the Earth. Okay, and this is an idealistic situation, but a little difference. But a body frame is different from orbital frame with phi, theta, psi. This is a very small angle. Okay? Angle difference around XY, Z axis. So this formulation is just I showed you when we discussed about gravity gradient stabilization. Okay, so it is almost the same. Almost the two frames is almost the same, but a little difference, and this difference can be represented by phi theta psi around the XYZ axis. Okay, so then, sorry. Okay, so this is assumption, and then now I'd like to write each term one by one. The first omega can be omega represented in the body frame can be written as omega z is Okay, so it is the same as we did in the gravity gradient stabilization. That initially, so omega is summation of the rotational speed of the orbital frame plus body rotation with respect to the orbital frame. Okay, orbital frame rotation with respect to the inertial frame plus body rotation with respect to the orbital frame. So that is omega b, and is that this can be written as phi dot minus psi. Okay, and the omega 0 is a rotational speed of orbital frame. Okay, the omega 0 is a rotational speed of the orbital frame with respect to the inertial frame. Okay, as I said, orbital frame is rotating around the y-axis. Y is fixed in the inertial frame. Okay, and the x and z will be rotated. Okay, x and z axis will rotate, and the this rotational speed is omega 0. Omega 0 is orbital speed, orbital angular velocity. Okay, so this is Earth-oriented satellite, Earth orientation satellite. That is some plane such as the antenna located plane should be every time located toward the Earth. Okay, in order to do that, the satellite should rotate with the same speed as the rotational speed around around the Earth. Okay, and so in that sense, omega 0 is a rotational speed of orbital frame, which means angular velocity around the Earth, around the same omega 0. So maybe the y-axis is the rotational speed of the orbital frame is minus omega 0. So please consider the sign. It is minus omega 0. Okay, so in that sense, in the y-axis is minus omega 0 plus theta dot. Theta dot is a rotational speed of the body frame with respect to the orbital frame. So as I said, these two summation is body frame velocity. And the y-axis is very simple, but for the x and z axis, okay, so this omega 0 make a coupling between these two axes. So that means, so this is psi is coming here and phi is coming here. And if omega 0 does not exist, this kind of the coupling does not happen. But okay, because of this omega 0, x-axis and the z-axis has some coupling like this. So this value comes here and this value comes here. Okay, so this is a very typical characteristic. And for the spinning satellite case, and as I said in my spinning equation, omega x-axis and z-axis is of course coupled. Okay, has some relationship. In that case, okay, and this coupling is by way of rotational speed. That is at that case a spinning speed, spinning axis. Okay, and the spin speed is much faster, much quicker than the orbital frame rotation omega 0. So that means for the spinning satellite, x and z coupling is much stronger because this omega 0 is a spinning speed. But for the bias momentum system, the omega 0 is very small. Okay, just one orbit, one cycle, one rotation in one orbital cycle. One orbital cycle is something like 100 minutes. Okay, in the low Earth orbit case. Okay, and the geosynchronous case, it is 24 hours. Okay, so that means this omega 0 is just one rotation in 24 hours or 100 minutes. So that means it's very small. Okay, so this is the difference. For the spinning satellite case, spin around the y-axis, make a coupling of the x and z-axis. But at that case, this omega 0 is very fast. Okay, the spinning satellite rotates something like one rotation per 1 minute, 1 second, or maybe 10 seconds and so on, very fast. And so in that case, the coupling is much stronger. Okay, so please consider that. If the satellite rotates around y-axis, then the x and the z-axis will have some coupling. And the coupling strength is dependent on the spinning speed or the rotational speed of the y-axis. Okay, so that is a very basic characteristics of the spinning satellite. Okay, and then so this is one, and now I'd like to write the total h. H is angular velocity, angular momentum of the total satellite. Can be written as okay. So it is a summation of the body angular momentum plus the wheel angular momentum. Okay, body plus wheel. Okay, and the now the h is represented in the body frame. Then we can write. So as I said, inertia tensor omega x, omega y, omega z, plus internal wheel is this one, okay, hx, hy, z, and so plus 0 minus h0. Okay, now we'd like to derive the differential equation of the omega x, omega y, omega z. So that is so this is a torque from outside, mx, my, mz, and the right hand side equation is hb sorry. Okay, as usual, so we have this formulation. So this is a relative differential. That means the change of the h with respect to the body frame. With respect to the body frame, which is represented in the body frame. Okay, so this relative means with respect to the body frame. Okay, and the so in order to make compensation, we should add the additional term of omega cross. So this is what we said many times. Okay, and so and this differential can be easily made, that you can put omega x dot, omega y dot, omega z dot, and so on. So it can be written as inertia tensor times omega x dot, omega y dot, and omega z dot. Plus, so this is only 0 minus h dot 0. Okay? And the plus omega cross inertia omega x, omega y, omega z plus 0 minus h0. Okay, so this is the equation. And then you should expand this right-hand side by making this kind of the cross product, and so this kind of matrix multiplication and so on. Okay, and then the final equation is something like this. So first, I'd like to write all the equation without any cancellation. Okay, and then we can write mx equal y2 dot Okay, I'd like to check. Okay, it's correct. And so in this case, we don't assume in this formula we don't assume that the internal angular momentum, that is a 0 minus h 0, is now here represented by the only hx, hy, hz. So it is. So this shows a more general term. So this is a more general equation, assuming internal angular momentum of hx, hy, hz transpose. Okay, so in case you have the additional momentum wheel, not only with the y-axis, but if we have hx, x-axis, and z-axis, then you can use this formula. Okay, so this is a more general equation, assuming that internal angular velocity, angular momentum is like this. And now we have the we would like to use the assumption. Okay, and now we use the assumption. that the first one is hx hz equal 0 and hy equal minus h. So maybe in this case the term concerning the hx hz should be 0. So something like this, hz, and the also z y z, okay, and z. Okay, so g's value can be 0 in this assumption. Okay, so like this. And the another assumption is that okay, and internal moment, angular momentum, that is hy is larger, much larger as compared with internal angular momentum is much larger as compared with a body angular momentum such as I bats means ixx or iyy or izz, and the times omega 0. Okay, omega 0 is as I said, the rotational speed of the body. So this is only the one rotational cycle in the one orbital cycle. So it's very slow. So that means omega 0 is much smaller as compared with the internal angular momentum of h. Okay, so only the h-related term will remain. Okay, in this formula. For example, maybe so this term should be deleted. Okay, should be deleted, and this term should be deleted, and so on. Okay, and finally we can obtain. Okay, let us write it here. And finally, we can have mx Okay, now I can write this. So much simpler form. Yes. And okay, so now let us analyze the these analysis of this equation. First, let us analyze it qualitatively. Okay, so first I can say that for the y-axis, around the y-axis, let us discuss about a y-axis, dynamics of the system. And maybe you can see that there is no phi and the psi appears in the y-axis equation. That means y-axis is independent from the other two axes. Okay? So it is independent. Okay? And maybe you can see that phi as only the theta 2 dot and the theta. And the h dot appears. And so this h dot, that is a change of the internal angular momentum around the y-axis. That means that h is, as I said, that's multiplication of the IW, moment of inertia of the wheel, times large omega. Large omega is the rotational speed of the internal wheel. So, okay, h dot means change of the speed of the reaction wheel, momentum wheel. So by changing the speed of the momentum wheel, it will generate some control force, control torque. Okay, so that means h dot can be used for control because we have the h dot term here. Okay, so and I'd like to go into detail later. And on the other hand, x and the z-axis has some coupling. Okay, and as I said, x and z-axis has a coupling because of the rotational speed around the y-axis. That is omega 0. But as I said, omega 0 is very small. Okay, as compared with the spinning satellite. Spinning satellite case, x and z-axis, coupling is made by spinning speed of the y-axis. But in this case, only the x and z-axis is coupled with the term of omega 0. It is small. But maybe you can see that this is here. If there is some internal momentum, okay, then x and z-axis is coupled by this kind of the internal momentum. So the coupling occurs by internal momentum h. So this is a feature of the bias momentum satellite. If there is no internal momentum, then only the x and z axis is coupled with omega 0, as I said. But if there is internal momentum, so this is much larger, as I said, internal momentum, angular momentum is much larger than this kind of I bats omega 0. So actually the x and z axis is coupled, okay, by internal momentum h. This is much larger. Okay, so this gives the control of the x and the z axis with a special consideration. You should make a special consideration about x and z axis control by considering this kind of the coupling, okay, by h. Okay, and the other term is almost the same, very similar. Okay, only the psi 2 dot and psi, theta 2 dot and theta, phi 2 dot and phi. Okay, so this is a qualitative, not quantitative, qualitative analysis of the three equations. Okay, now I'd like to consider the control system design. Okay, control system design. Now let us start with the y-axis. Okay, in the y-axis. Sorry. Okay, so as I said, the control torque can be obtained by h dot. Okay, that the changing of the wheel speed gives some control torque. And so even if there is no, outside torque, my, you can control the y-axis by way of this h dot. Okay, and then maybe the simple control law for the y-axis is okay, PD feedback. Can be applied. Okay, P means feedback of theta. Okay, and the D means a differential. That is theta dot feedback. So the control equation is control algorithm is something like okay. Theta is in this case k theta, and the control gain of theta dot is k theta tau theta. Okay, we have a two design degree of freedom. Okay, we have the two gain. Okay, one is a gain of the theta, and one is a gain of the theta dot. Okay, and now we write this kind of the feedback law. That is a control gain of theta is now denoted as a k theta, and the theta dot is k theta tau theta. Then we can write this kind of the feedback law. Okay. So if you write a block diagram of the total system is like this. Okay, so this is the total control system. Okay, now I'd like to show you, in more detail. And the theta, okay, is an attitude angle around the y-axis, and this y-axis attitude angle can be measured by some sensors. And so, what kind of sensor is used? Okay, so theta. Measurement can be made by, for example, the star sensor or earth sensor or sun sensor or magnetometer. Magnetometer means some sensor which can detect the Earth's geomagnetic field. And the geomagnetic field is already known beforehand. And so if the satellite measure the geomagnetic field direction with respect to its attitude, then the satellite can get the attitude information. Okay, the other sensor is the same. The satellite already knows some star's direction, and the the satellite measures the star direction with respect to its attitude. Then the satellite can get the information about its attitude. That is the star sensor. The same one is applied for the Earth sensor and the Sun sensor. So the theta can be measured by these kind of the sensors, and the theta dot can be measured by, this is only the gyro. Okay, there are several types of the gyro, such as a tuned dry gyro, or this is a mechanical gyro, but recently we are using the fiber optical gyro, or such kind of the optical gyros. Okay, so in any way, this theta and the theta dot is measured here, and it is going the feedback loop. So this is called the feedback loop. Okay, and the theta reference is this is a target attitude. Okay, so the theta reference is a target. Okay, we would like to make the y-axis attitude as theta reference. So this is a target. And this target attitude, and in this case, target for the theta dot equals 0. Okay, theta dot reference. Okay, so this is another target. Theta has a target, and theta reference has a target. Okay, and these two, okay, these value, and the actual theta and the theta dot is make difference. Subtracted. So these two value will be subtracted by theta and theta dot, which is actual value. Then we can obtain some difference. So this is a difference, okay, between the actual value and the target value. Okay. And then this difference has some feedback law. And then we can obtain, this is a H dot, how can I say, control H dot. Okay, so this is a required H dot. But there are some outside the disturbance torque. Okay, so you should add this MSY. MSY is denoted, represent for the outside disturbances. And so this MSY should be added here. And at this point, total torque comes here. Okay, the total torque is total torque consists of the H dot control, that is targeted or something like an intended torque using the wheel, plus some outside disturbance. This is non-intended torque. Okay, this is not happy torque, non-intended torque, and the summation is a total torque. And this total torque is going into the, so this is the dynamics of the body dynamics. Okay, so this is a feedback law. Okay, and the body dynamics means okay, so please write this. Total torque is divided by IYY. Okay, IYY, and the S square means twice. Okay, integration twice. That is a S square. Okay, so maybe you don't know about Laplace transformation. Okay, so I don't go into detail. Please study by yourself about the Laplace transformation, and later maybe you can understand what is this representation stands for. But anyway, at this moment, so S square means 2 times integration. twice integration. Okay, and then you can obtain the theta. Okay, so it's a kind of this kind of the loop. Okay, loop, occurs, and finally by making information loop. Okay, so this kind of iteration you can obtain the finally the h. So theta, that is the attitude of the satellite. Okay, and this is y-axis dynamics. And then the problem is how we can define these two, parameter. That is a gain of the feedback growth. So that is a control theory. Okay, and so I don't go into detail, but the next step is to how to design k theta and tau theta. Okay, how to design these two, control gain. How to design this value is another very important topics. And in order to find out good theta and k theta, is you can consider several factors to be considered. Okay, so if you make a controller system design, what factors you should consider? Please imagine. Okay. Maybe every time you make some control by yourself, you can use your body to make some control. Okay. So what kind of consideration you should make when you design a control system? Okay. Maybe the last year's participant can answer. Okay. So I'd like to ask you. Okay. How is it? The phone first. Tracking of what?
Tracking to the reference.
Okay, yes, tracking to the reference. So that should be maybe the second. Theta left, and theta left dot. Okay, that should be very important. So, okay, so if you make a certain theta left or theta dot left, so the system should, smoothly track this objective. Okay, if you make a first initial attitude and then change the different attitude target, and then the system should smoothly go to the different angle. That is a very important, capability of the control system. That is, of course, one factor to be considered. So, I have, one more important one in the first one. Maybe there should be several, things you should consider. Okay, how about you? Yes, stability. Yes. Okay, stability. Okay. Sometimes, if you make a bad control, the theta movement will oscillate, and this oscillation gets larger as time going. So initially it moves like this, but okay, in the meantime it goes this way. So this kind of the things happens if the stability is not assured. If stability doesn't exist, such kind of something like a divergence of the oscillation occurs. So in that case, the stability does not exist. And so first thing you should consider is the stability. Okay? How about you, In-kun? Disturbance? And please make more complete. Disturbance?
So when you control, there will be some disturbance to affect to the other control.
So please say a little louder.
When you control things, there should be some disturbance disturbance to affect on your control.
So, how you can do about the disturbance? So, please say more complete word. Sentence. Disturbance avoidance or disturbance suppression. You see?
I think it should be disturbance like the considerations.
Yes, disturbance consideration. Okay. So yeah, he's almost right. And so we say that suppress disturbance. Okay. So even if there is some disturbance torque, the satellite satellite attitude should be kept at the almost constant. So for example, if you are camera is directed toward a certain point on the Earth, and if some disturbance comes, such as collision with a debris and so on, but you should keep this camera direction, okay, statically. So this is something like a suppression of the disturbance torque. Okay, so this is another very important consideration. Okay, suppress the movement even there is some disturbances. Okay, so any other? Maybe. Okay, so if you have
Speed of conversion.
speed of conversion. Okay. Speed of conversion, but it's something similar to the number two. How speeds, how rapidly or how fast the system can track the target. Okay, so this also includes the speed of convergence. Yes, so that's another very important topic, speed of convergence. Okay, speed of convergence. That means, for example, as I said, so there is this kind of oscillation occurs, and we want to stop this oscillation. And how first you can stop this oscillation is very important one. Okay, sometimes it's very slow, suppression, but if you have a very good gain, then you can make like this. Okay, it's kind of the how first. The attitude movement can be suppressed is a very important consideration. Another one. What is another one? If we have. Okay, no. So the final one, maybe there are many, but only if we can pick up the very important 4 parameters for consideration, then the first one should be wheel speed limitation. Okay, because reaction wheel or momentum wheel inside of the satellite that has some limitation of the rotational speed. Okay. And so if you make a certain control law, this, and satisfy this H dot, then sometimes the rotational speed of the wheel may be very large. Okay, usually the wheel, rotational speed limitation something like 6,000 RPM or 10,000 RPM and so on. But by continually applying this kind of the control law, sometimes the reaction wheel speed may exist that limitation. In that case, no. Okay, so this does not work. That means that rotation speed of the wheel cannot excess the limitation, and when the wheel comes that kind of the limitation, then you cannot get any more controlled torque. So this is called the saturation. Okay, and you should also consider about that. Saturation. Okay, saturation. Okay, so if you continually apply this kind of the control law, okay, as I said, then the wheel speed may be very large. Okay, so this is a time, and this is a control speed of the wheel speed of the internal momentum wheel. So that is a large omega. Okay, so initially it may be usually the 3000. This is RPM. Nominally, for example, it is 3000, and the limitation is about 8000. So this is a limit. Okay, if you use this kind of the very typical wheel, and then by making this kind of the control, then it goes like this. But at some point, if it reaches a limitation, upper limit of the speed, then at this moment, no more control torque is generated. Okay, no more control torque is or can be generated. Okay, so at this point, the internal wheel is useless, gets useless, becomes useless. Then how you can, resolve this solution, this problem? How you can solve this problem? Okay, even at this point, still there are some disturbance torques from outside comes, and then you should control using the internal wheel, okay, in order to keep the attitude. But at this point, no more torque can be generated by the internal wheel. Then how you can do that? So is there someone who knows the answer? Okay. With what? Dumbbell? Sorry. Okay.
Maybe by using a damper for the wheel.
Damper?
Yeah.
What kind of the damper?
Like magnetic torquers can damp the.
Yeah, torquer. Okay, yes, exact. True, you are true. But not the damper. Okay, so when the wheel speed comes to this limitation, then you should add some intentional outside torque. Okay. Torque should be added. Okay, and the intentional outside torque will be generated by, there are several ways. First one is a magnetic torque or thruster, attitude control thruster. Okay, if you have this kind of outside torque, then okay, so this limitation will be relaxed. That means the wheel speed comes back to like this. Okay, and so this is the maybe so we don't want to pass the zero line. Maybe until the very small or until this nominal value. Okay, like this. Okay, and then the wheel speed change again from here, and so at some point it again goes up. Okay, so why this kind of the growing of the wheel torque, wheel speed occurs means that it comes from the disturbance torque. Is if the disturbance torque is the same direction almost all the time, okay, then the wheel speed grows up. Disturbance torque from the outside is oscillating. Then of course this wheel speed will oscillate. But if the disturbance torque is almost all the same time, then almost all the same direction, then in order to deal with this disturbance torque, the internal wheel speed grows up in one direction. Okay, and at this point, so you can add intentional outside torque. Okay, then the speed will get low. And again, if the disturbance torque, okay, comes in the same direction, then this kind of the growing up of the wheel again. So in that sense, important thing is that from this analysis, we can say that only wheel momentum wheel only system. That is the system control system which only has a momentum wheel. Okay, that seems to have control capability, but if this kind of the outside torque comes in the same direction almost all the time, then it eventually get to the saturation point, and at this point, the internal momentum wheel is useless, gets useless. Okay, so momentum wheel only system is not enough. You should add magnetic torque or thruster. Okay, so then the system is complete. Then the system is perfect. Okay, so this is very important. Okay, only momentum wheel is not enough. You should add magnetic torque or thrusters in order to deal with this saturation problem. Okay, and so this phenomena is called, as I said. Please remember this word, saturation. Okay, saturation. The wheel speed gets the maximum value, and you cannot get any more controlled torque. This situation called the saturation. And so this process is called. There are several ways to call the desaturation. Okay. Desaturation. So de means remove or something like that. Saturation, remove saturation, desaturation, or sometimes it is called momentum unloading. Okay, momentum unloading. So at this point, the reaction wheel has a lot of load, okay, on its back. And the unloading means throw away the this kind of the load, big load. So this is called unloading. And in this case, a momentum. So it has a big momentum here, and so this big momentum is leave on the ground, and so something like unloading. So it is called a momentum unloading. Okay, and so this is a very important process. So if you design a satellite. So the momentum wheel is not, usually maybe we will implement a reaction wheel, okay? For the Hodoyoshi satellite and Uniform satellite has a reaction wheel. But only that system is not enough. So in order to make this kind of desaturation, we implement a magnetic torque. Okay? Magnetic torque is very simple. Okay, just making a current, electric current through the coil, then it can generate magnetic momentum which interact with the geomagnetic field to obtain some outside torque. So that kind of a system should be added, okay, to the momentum wheel. So this is a very important result. Okay. Okay. So now I will conclude this bias momentum system analysis. Okay, and please study about the control system design. Okay, so maybe you don't have any knowledge about the this kind of the Laplace transformation and so on, but this is very basic information, and so please study about the basic fundamentals of the control system design. Okay, this kind of the block diagram, Laplace transformation, and so some design method such as a board diagram or Luto locus, okay, something like that, or Nyquist diagram and so on. So that is very important fundamentals of the control system design. So please, study by yourself. Okay, so I don't go into detail now. Okay, so now, we would like to finish the bias momentum system. Okay. Okay, is it okay to delete? Okay, now we'd like to go to the 4.4. Zero momentum stabilization. Okay, so maybe from the previous discussion about the bias momentum system, then we can make hx, hy, hz equal 0. Okay, that is the internal angular momentum is 0. Then we can obtain the equation for the zero momentum stabilization. Okay, I can write the equation, but in this case, h is 0. So we deleted many items by considering h is larger, very much larger than the other factors. But if the h is 0, then that kind of the factors which were deleted in the bias momentum system, appears again. So it has several terms still remains. Okay, and the okay, so like this. And in this case, maybe you can see, so G's term is, for the gravity gradient, torque. This is the outside disturbance torque. So this is already included in this figure. Okay, and in this case, again, as the satellite rotates around the y-axis with a speed of omega 0, then we have the coupling term like this. So just like bias momentum system, this is a coupling term. So we have the psi dot here, and we have the phi dot here. Okay, so the x and the z-axis is coupled. Okay. And the y-axis is, of course, independent from other two axes. Okay, so only the theta appears in the second term. Okay, and the in this, zero momentum stabilization system. So what is control force generator? And control force is usually generated by the reaction wheel at each axis. Control torque is given by reaction wheel. Okay, so okay, so this kind of the control algorithm or control law is used for each axis, and this okay. This kind of the required torque for each axis is calculated by this control algorithm. Okay, and so this is again the PD feedback. Okay, phi theta psi is feedback by the gain of k phi, k theta, and k psi, and the dot, that is a rotational speed, is also feedback by way of k phi tau phi, k theta tau phi tau theta, and k psi tau psi. Okay, and these control torque, desired or required control torque, is first calculated by this control equation, and then this torque is generated by the reaction wheel. Okay, reaction wheel at the of each axis. Okay, so that's it. It's very simple. So in this case, maybe you don't care much about this, coupling. Okay, because it is very small coupling between the x and the z axis, because omega 0 is very small. So you only have to think by each axis independently. So, and you can find out a very good control gain, okay, for each axis independently. Each axis can be considered independently. independently. Okay, so the control algorithm is very simple. That is very different from the bias momentum system. Bias momentum system case, x and z axis is coupling is stronger because not omega 0, but the h. Okay, there is an internal angular momentum around y-axis make a very strong coupling between the x and z-axis for the bias momentum system case. But for the zero momentum case, that h does not exist. So only the small coupling occurs by way of omega 0. But it is small. So we can, we don't care about this kind of interaction. And only you can, consider each axis independently and find out a good, feedback gain. Find out a very good feedback gain for each axis. So this is the case for the zero momentum. But you should also consider the saturation of the reaction wheel because it is controlled by the reaction wheel. Okay, so the reaction wheel has some point saturation. So you should also add magnetic torque or thruster to obtain outside torque for each axis. So the saturation also occurs. And so you should add, magnetic torque or the thrusters for each axis in order to avoid such kind of the saturation of each axis. Okay, so need magnetic or thrusters. For all the three axes. Okay, so this is very simple. Zero momentum system is very simple, just like that. Okay, important thing is that you can only consider each axis separately, independently. Okay, and similarly with the bias momentum system, you should consider the saturation. You should deal with some method to avoid the saturation. Now, I'd like to give you some, additional information using this, handout. Okay, and maybe it covers maybe all the, courses which I gave you up till now, and maybe it gives you in more detailed information. Okay. The first one in the table 4, so I'm sorry it is in Japanese, but maybe you can see the left-hand side, the top of the first page, the left-hand side that's satellite name, and please add by English, please. The first one is a satellite name, and second one is a launch year. And the third one is objective. Okay, the top two is the same, that is Earth observation. Okay, and the third one is X-ray astronomy. Fourth one is astronomical observation. Fifth one is international communication. And the sixth one is domestic communication. Okay, and the seventh one is maritime observation. And the final one is engineering test. Okay, and the fourth column is orientation accuracy, attitude control accuracy, and you have the three values. As the first one is the roll accuracy, and the pitch accuracy, and the yaw accuracy. Roll means around the x-axis, pitch means around y, and the yaw means around z. Okay. And the third one and the fourth one is all the axes should have the same accuracy of 0.017 or 0.01 arc second. Okay, so maybe you can see that the roll and the pitch is higher accuracy than the yaw axis. Okay, you can see almost all the Earth observation satellite or communication satellite each has the, for example, the first one is a roll and pitch is 2.1, but the yaw axis, accuracy is just 3. And please see the fifth one, that is an international communication satellite. Is roll and yaw is 0.11, and the yaw axis is much degraded, just 0.3. Okay, it is much relaxed, requirement. And why? Why the yaw axis is usually gets lower, lower accuracy requirement? Why? Please consider that yaw axis is, z-axis. Z-axis is, orbital, in the orbital frame, it is towards the center of the Earth. That means that, your stability, your requirement is that, I'm the satellite and you are the, the Earth, and then this axis is the yaw axis, and the accuracy around the z-axis means this rotational accuracy. That rotational accuracy is less, stringent, relaxed. Maybe you can guess why. So someone and who know this, we can answer this. Okay. If the, so I'm the, communication satellite, and you are the, ground system. So you are the target. And if I have a, error in the roll and pitch axis, what happens? So this is antenna, bore side, antenna direction. If we have a, pitch axis error, then the antenna direction moves like this. And if we have a roll error, then the antenna, moves like this. Okay? And if we have a yaw error, then the antenna moves like this. So maybe you understand. So your axis does not, strictly control. Okay? Because it's only the rotation. Okay? Even if the satellite rotates around your axis, maybe the, antenna or camera direction does not change very much. So in that sense, your axis usually has a less, stringent requirement. Okay, so and we go to the third one, and please you see the second and third one, and the second show the this is the Earth-oriented or Earth-oriented satellite. The satellite every time in this case some antenna or some camera is every time going toward the Earth direction. Okay. And then in the number 3, and what happened? Okay, what is angular velocity? The angular rate. The vertical axis shows the angular rate. The horizontal axis shows the time. And when the in the number 2 case, that's the Earth-oriented satellite case, if the orbit is different from the circular orbit, then how the angular rate change by time? So please see the number 3. 0 means eccentricity is 0. That is circular orbit. In that case, the angular rate, in order to achieve the Earth-oriented direction, is kept constant. Okay, of course. Okay, so this is a very important thing for the circular orbit. Why we use the circular orbit is that once we can obtain the Earth directed orbital rate, orbital or rotational rate, then it can be kept constant. But if the eccentricity gets larger, 0.05, 0.1, 0.2, 0.3, then the angular velocity should be changed, okay, periodically, okay, depending on the position of the ellipse. Okay, maybe you see it's very easily. Okay, so that's why we want a circular orbit. Okay, it's very easy. Once you can get a rotational speed of the satellite, so that speed should be kept constant, should be kept. Then we can obtain the Earth-oriented attitude of the satellite. Okay, so the number 4 is an example of the disturbance torques. Maybe so. Almost all of them I already showed you. The first one is okay, astrodynamic. Astrodynamic. What is astrodynamic? I don't know. Astrodynamic is this is gravitation from the third body. The third body means not the Earth. For example, the gravitation from the sun or gravitation from the moon. But this disturbance torque does not have the effect on the attitude. Okay, it only has the position. Okay, and the magnetic disturbance torque. Okay, as I said, the satellite has a magnetic momentum, and it interacts with the geomagnetic field, and it gets some disturbance torque, and the gravity gradient, and the solar radiation, and the thrust misalignment. Okay, the thrust does not emit power to the desired direction, but it has some error always. And so this gives some misalignment. This gives some disturbance torques. Okay? And the internal torque force means a mechanism. So if you move something inside of the satellite, then it gives some disturbance. And fuel movement, which is called the sloshing. And astronaut movement. So this is some human-tended system, such as a space station or space shuttle. Astronaut movement gives some disturbance. And the flexible appendage, okay, and the or other general mass movement, okay, something like that. Okay, so if you move something inside of the satellite, that is the rigid system does not allow such kind of the movement inside of the satellite, but this kind of the movement occurs. These will give some disturbance torques to the satellite. Please see the number 5. Okay, so this is a feedback loop of the control system. The spacecraft has some attitude, and this attitude can be measured by the attitude sensors. Okay, and the onboard computer calculate just like that some control torque. This is a feedback using the feedback control law, and this torque demands comes to the control torque, such as a reaction wheel, momentum wheel, or magnetic torque, or thrusters, and it gives some torque to the spacecraft. So this is a kind of the loop, control loop. Okay, and now go to the next page. So this shows the growth of the Intelsat system, Intelsat series. Intelsat is a communication satellite above the Pacific Ocean or Atlantic Ocean. It can connect the information from the United States to Japan or United States to the Europe and so on. Okay, and the first 3 satellite is spin satellite, single spin satellite. Okay, and in the single spin satellite case, the inertial moment of inertia around this spin axis should be the maximum. Okay, as I said. Otherwise, the spin axis will be changed. But from the 4 and the Intelsat 4, it became dual spin satellite. Maybe you can have a small gap at the center of this long cylinder. Okay, and that is that separate the platform and rotor. And as I said in my lecture, this kind of the long cylinder can be possible in this dual spin satellite. And the fifth 5, Intelsat 5 is a 3-axis stabilization. This is a bias momentum satellite. Okay, and the 6, again, it became dual spin satellite. Okay, so dual spin satellite has 2 meanings. The one meaning is that this kind of long cylinder is possible, okay, without violating the stability requirement. Okay, so this is very good for install in the rocket fairing. Another a merit of the this kind of dual spin is that you have the platform which does not rotate very fast, and so you can implement this kind of the antenna or camera at the part of the platform because it does not rotate very fast. Okay, so this is a dual spin satellite. Okay, and the number seven is axis definition, and the orbital frame is yaw axis directed toward the center of the Earth, and the pitch axis, that is the y-axis, is perpendicular to the orbital plane, and the x-axis is usually toward the velocity vector direction. Okay, and the eighth one is just a formulation of the schematics of the dual spin satellite. So, and go to the next page. And next page is a bias momentum system. And as I said, in this case, the momentum wheel is fixed along the y-axis because only the y-axis remain constant. Okay, but the x-axis and the z-axis rotate. Okay, in order to make Earth orientation motion. And number 10, this is a reaction wheel. So this is a zero momentum system. So you can put, x, y, z axis reaction wheel. But in this case, you have the fourth reaction wheel that is called intermediate reaction wheel. Why? Why you have the fourth one? Only 3 are enough in order to get the control torque around the 3 axes. But why we have the fourth one? Okay.
We can repair this if something happened to.
Yes. Yeah. So this is called the redundancy. Okay, redundancy. If something happens or some wheel fails, then the fourth one can provide some control torque around that axis. And the why this kind of the skew direction of the wheel? This is because in this kind of the skew wheel can generate the torque of the 3 axes. Okay, not the 1 axis, but it can provide the torque for the 3 axes. So this kind of the 4 wheel configuration is very typical for this reaction wheel. So our HODOYOSHI satellite and the Uniform satellite has a 4 wheel configuration. Okay, and the XYZ, and the last one is a skew. Okay, and the 11 is configuration of the attitude thrusters. Okay, so we don't go into detail. And the 12 is spin axis precession and nutation. Okay, and the precession means change of this nutation angle. Okay, and the nutation is something like this kind of the wobbling motion of the satellite. Spin axis is rotate around the total angular momentum direction, and the spin still exists. Okay, the satellite rotate around the spinning axis. So this dual motion is called the nutation, and the nutation angle change. This is called the precession. Okay, let's go to the next one. So this is an example of the thruster system. I didn't tell you very much about that. And the upper part is performance of the different kind of the thrusters, and the value shows the ISP specific impulse. And if you have a higher value, then you can get larger delta V with small amount of fuel. For example, ion thruster is a maximum that it has a very large ISP of the 3000. Okay, if you use the ion thruster, you can get a very high orbital maneuver or attitude change capability with very small fuel. Okay, but that torque itself, force itself is very small, just like 1 millinewton or less than 1 millinewton. Very small torque or very small force, but it can it is very effective and efficient. Okay, the other two is configuration of the thruster system. And let's go to the page 5. Okay, so the upper part is a magnetic field flux density, that is a B, which in my lecture, B dependent on the altitude. Okay, if the altitude gets larger, that is the right hand side, then the magnetic field flux density B gets quickly gets lower, gets smaller. Okay, and the lower part shows some reaction wheel. 16 is a spinning momentum wheel. So this is just like a spoke of the bicycle. Okay, in order to have a larger moment of inertia with small weight, you can concentrate the mass at the outside of the wheel. Okay. And so this kind of the wheel rotate with the speed of the very 3,000 RPM or 6,000 RPM usually in order to obtain the H. And this 17 is a very typical altitude sensor, reference sensors accuracy, star, sun, and Earth magnetometer, and the RF beacon is signal coming from the ground. Then the satellite can detect the direction of the coming beacon, then it can know its altitude. It's not so accurate, but about 1 arc-minute. Okay, and okay, let's go to the next page, page 6. This is a sun sensor, example of the sun sensor. Okay, and if the direction of the sun changes, then the photon detector on the bottom will be on and off, and then you can get the direction of the sun. Okay, so 19 is a sun sensor, and the 19 left 19 and the 20 is a sun sensor. Sorry, Earth sensor. So this is a case for the spinning satellite. Okay, and okay, please go to the next page. And sorry, so this is in Japanese. And 21 is gyroscope. The from left is a rate integrating gyro, and the next one is a rate gyro, and the right hand side is a 2-axis rate gyro. And the middle part is a optical gyro. RLG stands for ring laser gyro. It is currently the most precise gyro. Okay, this gyro is used for the launch vehicles such as H-2A. And the last one is a fiber optic gyro, FOG. It is fiber optics. Fiber. Optical fiber is rounded around a certain axis with a very long, such as a 1 kilometer or 2 kilometer size, fiber optics is circulated around a certain axis. Okay, and the Hodoyoshi and the Unihome used this fiber optical gyro. Okay, and go to the next page. So next page is okay. You don't have to. And the important one is the last page. Last page, maybe the upper part shows dependence of different kinds of disturbance torque on the altitude. The vertical axis shows the altitude and the log scale. Okay, and the horizontal axis shows the torque of each different disturbance torque source. And maybe you can see the vertical line, that is the disturbance torque whose strength does not depend on the altitude. The first one is specular reflection and diffuse reflection. That is solar radiation pressure torque. It does not depend on the altitude. Okay, and the one which is dependent on the altitude is gravity gradient. Okay, so that is R triple. Okay, it is proportional to the 1 by R triple. Okay, and so it gets quickly gets lower if the altitude gets higher. And the magnetic torque is almost the same. Okay, it also proportional to the R triple 1 by R triple. R is a distance from the center. Okay, and it quickly gets smaller. And this line, slanted line, is aerodynamic. Okay, aerodynamic. Okay, it is a straight line. So it depends on the sunspot minimum, sunspot maximum. That means it depends on the solar activity. If the solar activity is very strong, then the disturbance torque gets higher. Okay, something like that. Okay, maybe you can see like that. And as I said, solar radiation pressure torque, and the aerodynamic torque will almost be the same at the altitude of 1,000 kilometers. Okay, and maybe it has some cross point between these two factors, aerodynamic and the solar radiation pressure torque occurs at around the maybe 800 or 1,000. Okay, in the log scale around 3. Okay, 1,000. Okay, it cross. So below this height, you should mainly care for the aerodynamic. Okay, and above this height, you should mainly care for the solar radiation pressure. Okay, that's it. So okay, so I'm sorry. So the 10 minutes already passed, and so I'd like to conclude the first lecture. Are there any questions? If no, let us have a 10 minutes break. So let us start the next lecture from 10:50.